The art of balancing efficiency and complexity in algorithm design. In the world of computer science and software development, algorithm design stands as a cornerstone discipline that determines how efficiently problems can be solved through code. This intricate field requires balancing various factors such as time complexity, space requirements, scalability, and maintainability. Designing effective algorithms is both an art and a science. It demands creative problem-solving skills alongside rigorous mathematical analysis to ensure optimal performance across different scenarios. Fundamental principles of effective algorithm design. An effective algorithm must first clearly define the problem it aims to solve. Understanding input constraints, expected outputs, and edge cases forms the foundation for designing robust solutions. Clarity in objectives helps prevent unnecessary computational overhead. For instance, sorting algorithms may vary significantly based on whether they need stability or memory efficiency. Divide and conquer strategies often provide elegant solutions by breaking complex problems into smaller subproblems. Merge sort exemplifies this approach through its recursive partitioning technique. Greedy approaches make locally optimal choices at each stage, which might lead to globally optimal results under certain conditions. However, these methods require careful validation against potential counterexamples. Time complexity, measured using big O notation, it indicates how runtime grows relative to input size. Algorithms with lower asymptotic bounds generally perform better on larger datasets. Space complexity refers to additional memory usage beyond input storage. In-place operations are preferred when possible to minimize external memory consumption. Maintainability becomes crucial as systems evolve over time. Well-documented algorithms with clear modular structures facilitate easier updates and debugging efforts later in their lifecycle. Evaluating time versus space trade-offs. Selecting between faster execution times and reduced memory footprints often involves trade-off decisions tailored to specific application contexts. For example, caching mechanisms utilize extra memory to store frequently accessed data items, thereby reducing repeated computation costs during subsequent queries. Hash tables demonstrate this principle effectively by sacrificing some memory for constant time lookup capabilities compared to linear search implementations. Cache-friendly algorithms optimize spatial locality by arranging data access patterns to maximize CPU cache utilization, leading to significant speed improvements without increasing actual memory footprint. When dealing with limited hardware resources, developers must prioritize either temporal efficiency or spatial economy depending on system constraints and user expectations. This evaluation process typically begins with identifying critical bottlenecks within existing implementations before considering alternative designs that address those issues effectively. Optimization techniques across different problem domains. Different types of problems demand specialized optimization techniques suited to their particular characteristics and limitations. Numerical computations benefit from parallel processing frameworks that distribute workloads across multiple cores or machines simultaneously. Graph traversal algorithms employ breadth-first search, BFS, or depth-first search, DFS, methodologies depending on whether shortest paths or connectivity information is required most urgently. Data compression routines leverage entropy encoding schemes like Huffman coding to achieve high compression ratios while maintaining decompression feasibility within acceptable limits. Cryptographic functions rely heavily on mathematical hardness assumptions, ensuring security even against powerful adversaries attempting decryption attempts. Machine learning models use gradient descent variations optimized for convergence rates, regularization strategies preventing overfitting, and dimensionality. Reduction methods simplifying feature spaces. Bioinformatics tools apply dynamic programming principles combined with heuristics to manage sequence alignment challenges involving massive genomic databases efficiently. Design patterns that enhance algorithmic performance. Several established design patterns contribute meaningfully toward improving overall algorithm effectiveness across diverse domains. The memoization pattern stores previously computed results to avoid redundant calculations, commonly used in recursive function calls where overlapping subproblems exist. Lazy evaluation postpones expensive computations until absolutely necessary, optimizing resource allocation by deferring costly operations until they become essential. Pipelining allows concurrent processing stages working independently yet sequentially towards final outcomes, maximizing throughput similar to assembly line manufacturing processes. Hybrid architectures combine multiple approaches dynamically based upon real-time feedback regarding current workload characteristics. These patterns help create adaptable systems capable of handling varying degrees of complexity gracefully while maintaining predictable performance profiles under typical operating conditions. Proper implementation ensures these patterns complement rather than complicate underlying logic structures, preserving clarity amidst increased sophistication levels. Testing strategies for verifying algorithm correctness. Rigorous testing protocols play vital roles in confirming algorithm correctness and reliability prior to deployment phases. Unit tests validate individual components behave as intended under controlled environments, simulating varied inputs systematically. Stress testing exposes weaknesses by subjecting algorithms to extreme parameter values, pushing boundaries beyond normal operational ranges. Fuzz testing employs random, invalid inputs aiming to trigger unexpected behaviors, revealing hidden flaws lurking beneath surface-level functionality. Formal verification provides mathematically proven guarantees about correctness properties, assuming precise specification definitions hold true throughout entire execution flows. Combining these complementary test suites offers multidimensional assurance covering functional accuracy, robustness against failures, and compliance with specified behavioral contracts. Case studies illustrating real-world applications. Real-world applications showcase how theoretical concepts translate into tangible benefits within practical settings. Google's PageRank algorithm revolutionized web searching by employing matrix multiplication techniques, iteratively converging towards stable ranking distributions reflecting link popularity metrics accurately. Twitter implemented tweet recommendation engines leveraging collaborative filtering mechanisms, analyzing vast amounts of social media activity data efficiently. Netflix streaming services utilize personalized movie suggestions powered by advanced machine learning models, predicting viewer preferences based on historical watching habits precisely. Airlines schedule flight routes applying graph theory optimizations, minimizing fuel consumption while adhering strictly to safety regulations governing airspace management procedures meticulously. Healthcare institutions deploy diagnostic support systems incorporating Bayesian inference networks, assisting doctors interpret medical images reliably despite inherent uncertainties present naturally within biological samples examined closely. Each case demonstrates successful integration of sophisticated algorithmic ideas addressing domain-specific challenges creatively yet practically applicable at scale seamlessly. Evolving trends shaping future directions. Emerging technologies continue influencing directions taken forward, shaping future developments, continuously evolving rapidly. Quantum computing promises breakthroughs enabling exponential speedups, solving currently intractable problems through novel qubit-based architectures challenging classical paradigms. Fundamentally, neuromorphic engineering seeks bio-inspired designs mimicking human brain functionalities, potentially surpassing traditional silicon-based processors' limitations eventually. Edge computing decentralizes data processing closer to source locations, decreasing latency concerns associated with centralized cloud infrastructures traditionally relied upon heavily recently. AI-driven automation accelerates prototyping cycles, allowing rapid experimentation, exploring numerous possibilities, quickly narrowing down viable options swiftly. Sustainable computing initiatives emphasize energy-efficient practices, reducing environmental impacts caused unintentionally by ubiquitous digital infrastructure expanding exponentially worldwide constantly. Keeping abreast of these trends enables practitioners to anticipate upcoming challenges, proactively adapting skill sets accordingly, staying relevant amidst technological transformations unfolding daily relentlessly. Conclusion: mastering algorithm design requires deep understanding of core principles guiding decision-making processes involved throughout entire development lifecycles comprehensively. By thoughtfully evaluating trade-offs among competing priorities like performance versus simplicity, we can craft solutions meeting real-world needs, effectively achieving desired outcomes consistently.